This video is intended to illustrate basic principles in solving inequalities where you can't just isolate the variable x. The problem that I've chosen may be a little more difficult than usual in order to illustrate some of these principles. We're interested in solving the inequality where 1 divided by x minus 3 is greater than or equal to 2 minus 1 divided by x plus 1. In order to solve this inequality, we'll do a bit of algebra. However, first I want to make sure that we understand the basic principles of what it means to solve an inequality. The easiest way to illustrate that is with a graph. Here's a graph of our two expressions. In purple, we have expression 1, which I'll call y1, which is 1 over x minus 3. Our second expression, which is shown in orange, and I'll call it y2, is the expression 2 minus 1 divided by x plus 1. To solve the inequality, we're interested in answering the question, when is y1 greater than
In other
or
words,
equal to, we want to know
y2.
when the purple graph is above or intersecting the orange graph. As I look at the graph, I can see that for many x values, for example, this point here at -7, the orange graph is above the purple graph, and so this point would not be in our solution set. However, at a point close to -1, I can see that the purple graph is actually above the orange graph, and that point would be in the solution set. As I go across the x-axis, each point I could basically say it's in or it's not, and only a few points make it look like y1 is actually greater than or equal to y2. A solution set corresponds to finding an interval. And so it appears that there's a small interval here near -1, and there's another small interval here near the value x equals 3. Now intersecting corresponds to the point where the two curves cross, which correspond to the right endpoints of our intervals, and the left endpoints correspond to these points where it switches. And it's not really clear where those are, just from the picture anyway. And so my solution set needs to be able to describe the set formed by these two intervals. Algebra will allow us to determine the exact coordinates of those 2 points for each interval. Alright, let's start by looking at the algebra. Many of us don't like these fractions, myself included. They're sort of bothersome. But unfortunately we have to deal with it. Many students want to get rid of fractions by cross-multiplying. The problem is that this doesn't work for inequalities. The problem is that when I cross-multiply, for example, if I multiplied both sides by x minus 3, I'd be multiplying by an expression that includes the variable. If that expression is positive, the inequality stays the same. But if that expression is negative, the inequality will reverse. Because I don't know what x is, I don't know whether the inequality stays the same or reverses. And so multiplying by a variable expression has the potential of completely changing our inequality. We need a different strategy. The strategy that we'll take is that we'll move everything to one side so that our relationship is with 0. Then we can use factor sign analysis. Why is this the strategy that we use? Because if I know the factors and their signs, then I can count how many are negative. Knowing how many factors are negative allows us to determine if the product is positive or negative. If there are an even number of negative factors, the answer is positive. If there are an odd number of negative factors, the answer is negative. So for our problem, we need to move everything to one side. So we'll need to subtract 2, so 1 over x minus 3. We'll subtract 2, and we also need to add 1 over x plus 1. And our new inequality is now related to 0. We have an expression is greater than or equal to 0. By comparing it to 0, we want either positive or 0 values. Our expression as written is not factored. So we'll need to group our terms together by finding a common denominator, and then we'll need to factor. In our expression there are two divisions. One is to divide by x minus 3 and the other is to divide by x plus 1. Each term needs to have both of those division factors. The first has x minus 3, and so it's lacking the x plus 1, so we'll multiply and divide by x plus 1. Notice that we have to put the x minus 3 in parentheses. Subtracting 2 doesn't have any of those terms, so we'll need to multiply by both x minus 3 and x plus 1. On top and on the bottom. The third factor, 1 over x plus 1, already divides by x plus 1, but it doesn't divide by x minus 3. So we'll need to multiply top and bottom by x minus 3. We now have an expression with a common denominator. Each term is divided by x minus 3 and by x plus 1. That forms a common factor, which allows us to write this fraction as a single division. We have x plus 1 minus twice. Now let's take advantage of this time to multiply that out. I get x squared minus 2x minus 3. And our last term is we're adding x minus 3. All over the product x minus 3 and x plus 1. Notice that I did not multiply out the denominator. As I do my algebra, eventually I'm going to have to factor everything anyway, so why multiply it out if I'm just going to factor it again later? We make our inequality statement. It's still a formula is greater than or equal to 0, and now I can combine all my terms. I look at my x squared terms. In the numerator I have negative 2x squared. For my x terms I have x, I have plus 4x, and I have another x plus 6x. And our constants, we have 1 plus 6 minus 3 makes it plus 4 divided by x minus 3 and x plus 1. Put everything in proper parentheses, and we have a new inequality. It's not quite factored yet. My numerator still has a common factor of negative 2. I always like to factor out those negative constants if I can. So I get x squared. 6 divided by negative 2 is negative 3, so I get negative 3x. 4 divided by negative 2 is negative 2. At this point, we have a quadratic in the numerator, and as we look at our algebra, there is no clean factorization. And so we find that we have 4 factors for this problem. I have the factor negative 2. I have this quadratic factor, x squared minus 3x minus 2. I have the factor x dividing by x minus 3. And I have one more factor coming from dividing by x plus 1. What I want to do is I want to know where does each factor change sign. So for each factor, I might draw a number line. The factor negative 2 is always negative. The factor x squared minus 3x minus 2 is quadratic. We didn't see how to factor it, so we need to look for the roots using the quadratic formula. Sing with me. X equals negative b plus or minus square root b squared minus 4ac all over 2a. And so we find that we have two solutions. X equals 3 minus the square root of 17 over 2, and x equals 3 plus the square root of 17 over 2. In terms of decimal values, 3 minus the square root of 17 over 2 is approximately negative 0.5. You can get more decimal values from your calculator. And the formula 3 plus the square root of 17 over 2 is approximately 3.5. If I were to graph my parabola, those would correspond to two roots where I cross my axis. So I have two roots, one of which is here at 3 minus root 17 over 2, and the other is at 3 plus root 17 over 2. And from our graph of the parabola, we know that it's above the axis when I'm outside of the roots, and it's below the axis when it's in between. The factor that comes from dividing by x minus 3 has a root. Well, it doesn't actually have a root. It changes sign when x equals 3. So here's 3. If I pick a number greater than 3, for example 4, in effect multiplying by 1. If I pick a number less than 3, for example 0, I'd be dividing by 0 minus 3 is negative 3. I'd be multiplying by a negative number. Finally, dividing by x plus 1, there's a sign change at x equals minus 1, which is where x plus 1 equals 0. To the right of that point, this factor is positive. For example, if I pick 0, I'd be dividing by 1. If I pick a number to the left of negative 1, for example, negative 3 plus 1 is negative 2, I'd be dividing by negative 2 or multiplying by negative 1/2, and so I get a negative factor. In order to finish our sign analysis, we now need to find the intervals and count how many negative factors we have on each interval. So we'll form a new number line that comes from each of the factors combined. We have negative 2 times x squared minus 3x minus 2, and divided by x minus 3, and divided by x plus 1. Each point that we had in our number line above will appear. So we need to have our point at negative 1. We'll need to have our two factors from our quadratic, 3 minus root 17 over 2. We need our point at 3. And we need our second quadratic point at 3 plus square root 17 over 2. Our two factors from the quadratic, because they're in the numerator, I actually get 0. But at x equals minus 1, I would be dividing by 0. And so the point at negative 1 for our entire expression is undefined. Similarly, I'm undefined at x equals 3, because you can't divide by 0. Now let's count how many signs we have in each factor, on each interval. To the left of negative 1, our factor of negative 2 is always negative. Our factor from our quadratic was positive. Our factors for our denominator, the factor x minus 3, is negative. And the factor for x plus 1 is also negative. We have a total of 3 negative signs for an overall sign that's negative on that interval. In the next piece, let's look at our signs. We always have, well, we're sort of cramped. Let's put it up above. Negative 2 is always negative. We are still outside of our quadratic roots, so we're still positive. And our dividing factors are negative. And because I've crossed over the purple line, I now have a positive factor for a total of 2 negative factors. A negative times a negative is a positive. And so in this middle interval, I get a positive term. So as I do this on each interval, the negative 2 is always negative. Our quadratic is negative when we're between the factors, or between the roots, and are positive when I'm outside of the roots. Our division, our dividing by x minus 3 changes sign when I cross 3. And so to the left of 3 it's negative, to the right of 3 it's positive. And dividing by x plus 1, to the left of minus 1 was negative, and every term to the right it'll be positive. So let's count how many signs we have. In the middle interval we have 3 negative signs, that's negative. In this little interval between 3 and 3 plus square root 17 over 2, I have 2, and positive again. And to the furthest interval to the right has 1, which makes the overall product negative. My inequality wanted to know which values were positive or 0. So my solution will correspond to the intervals going from negative 1 to 3 minus the square root of 17 over 2, and from 3 to 3 plus the square root of 17 over 2. And I include the 2 points from the quadratic because those were the points where the curves intersected. Our final solution is given by the interval notation describing this set. Negative 1 to the point 3 root 17 over 2, not including negative 1, but including the quadratic union, the second interval, that goes from 3 to 3 plus the square root of 17 all over 2, including the second endpoint. And that's how we solve the inequality. The key steps were to move everything so that we can have a relationship with 0. In this problem we had fractions, so we needed to combine our terms into a single fraction with a common denominator so that we could factor it. Once we had our factors, we identified where our factors changed sign so that we could create a single summary, which is the number line at the bottom, that describes each interval whether my function is positive or negative. From this information, we can solve our inequality.